Hi, today I'm going to give you a very brief and superficial introduction to machine learning with Python. This is a very broad field which we cannot cover in any depth in this course, but the main idea is to show you how easy it is to use these tools with Python, especially with Scikit-Learn, which is the library we're going to use. And in this first hour, I'm going to focus on supervised learning. So basically regression and classification problems where we want to predict something using our data. I'm also going to talk a bit about the problem of overfitting if we're trying to learn aspects of our training set which do not generalize outside of the training data, and how we can check that and prevent that with cross-validation. So let's start with the basic idea of machine learning. The purpose here is to get a computer to make sense of the data, or help us make sense of the data. So this is an old idea from the middle of the 20th century, so it's old now, trying to give computers the ability to learn without having to tell them exactly what we want them to do. So a more formal operational definition is that we want a computer program, to learn from experience, from examples, and we know that it can do that if by some measure of performance the program improves as we give it examples at performing some task. So the basic idea is that we have some tasks that the system must perform. We know how to measure the performance on that task, and we have the data that we can use to improve the system's performance. And this can cover many different areas. So we can do regression, for example, if we want to predict some continuous value like prices or something like that. We can do classification if we want to separate our data into different classes. We can also do things like try to find association between different features or different entities, grouping things together with clustering, estimated density, and so forth. So there's a lot of things that we can try to use a program to learn from data and find these patterns in data. And the main usefulness of machine learning is to help us solve problems for which we do not have explicit rules on how to solve them. For example, if we want to identify handwritten digits, if we want to know that this is a 9, a 6, a 2, it's very hard to write a code that would explicitly follow some set of rules to classify these digits. But if we have lots of examples and labeled examples, we can try to abstract or extract some statistical correlations there that allow us to label correctly each digit. So this is good when we don't have explicit rules, when we have large volumes of data, for example, in data mining, or when we need to respond quickly to changing conditions. So, for example, personalization of the feed we get on social media. This is usually done by algorithms that are learning as the user interacts with the system, and it would not be feasible to have people programming rules, specific rules for different users or things like that, and trying to keep up with the patterns of use of that system. So basically, if we don't have a recipe for solving a problem, but we have the right data, machine learning can be a good option. So let's take a look in this first hour at supervised learning. The idea of supervised learning is that we have a data set, a set of examples that are labeled with the correct answer that we want. So when we are trying to find how to predict that target label, we can monitor what our learner is doing. So basically, we can feed the feature values to the learner. The features are those values that we predict we will have access in the future, and from which we want to try to estimate some target. So this is what feeds into the learner, and the learner will output a prediction for a target value. But since we have the target values in our data, we can now check how the learner is performing. is performing. So we can measure this error, the difference between what the learner is predicting and what the target is, and we can feed this back into the learner in order to improve the performance at predicting these values. And we can consider two broad different types of problems. So with regression, what we want to do is to find some function that approximates as much as possible the values in our examples, so that we can predict those values with a minimum of error. In classification, we have our examples separated into different categories, and what we want to find is some function that allows us to split data into any of those categories correctly. So there is a slight difference with what we're doing here, but in both cases this is supervised learning if we have the labels in our data, and so we can supervise how the system is learning. So one example would be for identifying faces. We can have a set of examples of faces, and then we teach the system to find the faces in photographs, so it can identify where faces occur. The basic idea in abstract is that we have this set of labeled data where we distinguish the X vector for each example to be the features, that is, those values to which we always have access and that we can use to estimate some target value. And the Y here is the target value that we want our learner to estimate. So each example is composed of any number of feature values and some target value that we want to approximate. And we have a set of examples. So in this case, we have n examples like this. And we assume that somewhere in the universe there is this f function, which we do not know, that maps the features into the target value. So if we had this function, we could feed in the features and have as output the target value. We do not know what this function is, but what we want to find with supervised learning is a set of parameters for some model. This G model represents a set of possible functions that we can obtain by instantiating these parameters. And so we want to adjust these parameters so that this parameterized function here, when we feed in the X, will output the Y. So basically, we want G to approximate this unknown F as much as possible by adjusting the parameters in G. So this is the abstract idea of supervised learning. And here we can see how we can supervise the training by optimizing these parameters here in order to minimize the error we are measuring in our training set. So this is the training error or empirical error, and it's the error we associate with each instance of our parameters that we adjust, and we adjust the parameter so that the error minimizes. So in classification, we have a discrete set of labels, and these correspond to different classes. For example, with spam detection, we may want to predict whether some email is spam or not spam. And in that case, we want to measure the performance of our learner by seeing how correct the predictions are, where the examples are placed, in which class the examples are placed. And so we want to learn some partition of the data that places the examples in the right places. If we are dealing with a regression problem, then we have some target value that we can think of as a continuous value, and we want to approximate as much as possible our predictions to that target value. So let's see. Let's start with regression. It's easy to picture. Let's consider polynomial fitting. We already did this last week. So we just adjusted polynomial curves to a set of points. So basically, we have this model here that describes a set of possible polynomial curves that we can obtain by instantiating these parameters. So we want to find the set of these theta values that best adjust our data. Suppose, for example, we are considering only a straight line. So this would be a polynomial of degree 1. We only have these two parameters. Now the question is, if we have these data points, how can we find the best line? There are many different lines here, but we need to have some measure of performance, some measure of how appropriate the line is to these data in order to optimize the parameters and find the best line. So this there is a bit of theory behind this, which I'm not going to go into, but if we assume that the target value is some function of x plus some error, some normally distributed error, so that this is an error with a Gaussian distribution, then we are assuming that the x values don't have error, the error is here, and each of these points is the result of that function we want to approximate plus some noise, some random noise we have here. And we want to compute these theta parameters in order for G, our model, to approximate f. So in this case, if it's a straight line, this is our model here, and we want this to be as close as possible to that hypothetical f that the universe has, which we do not know, but which can be used to predict, to output these values. Then under these assumptions, if the error is on the target value and it's normally distributed, then we have this maximum likelihood solution, which corresponds to minimizing the quadratic error. So if we measure the error between each point and the line, the difference between each point and the line, and use that squared, if we minimize the sum of this over all our training set, we get the line that makes it the most probable to have a data dispersion like that, if the line is correct. So this is the maximum likelihood model. I'm not going to go into much detail here, but this is just to get you an idea of, to give you an idea of how these things work. So we need to find the parameters, these theta 1 and theta 2, that minimize the quadratic error here. So let's visualize the surface of this error function with respect to these two parameters. We can think of it as something like this. If we go too far from the right combination of values, we start getting a very large error. If we are close to the right combination, we have a smaller error. So what we need is the kind of optimization algorithms we used last week to solve this kind of problem. We have our performance measure. In this case, it's the error. The performance is best when the error is smallest, and we want to minimize the error. So we start at some point, we go down the surface of the error function, and then we keep going down in different directions until we find the optimum value. So this allows us to find the best parameters for our model. Remember that our model was a straight line. It has two parameters, the inclination and the intercept here. So we find the best ones, but it's still not very good. The shape of this data does not seem to be a straight line. So now we can improve the model. But let's stick to linear regression. So the idea is the same. We have a linear regression because we have something of this form, one constant multiplied by one of the features, another constant by another of the features, and so on. So this is a linear expression, and we are doing a linear regression. But how can we make this straight line bend if we are doing a linear regression? The idea is that we can create additional features by using some nonlinear transformation on our data. So for example, instead of having only the x value and the target y, we can create two x values. So one of them is the original one, and the other is the original value squared. So this is a nonlinear transformation, squaring the value. And what this does is it gives us now the features in this plane. So this is the original coordinate here, and this is the square of the coordinate, and now everything is in the curve in this plane. And for each of these points, we want to predict the height here, which is the target value, for each of these pairs of coordinates. So we expanded our initial features into two features, the original and the square of the original. And now we can use a linear model in 3 dimensions. So basically we want to we want this two-dimensional hyperplane here, or two-dimensional plane that this expression describes, to be adjusted in three-dimensional space when we consider the two x values and the y, so that this approaches as much as possible the target labels for our data. So something like this. We can adjust the parameters to get this straight plane here that tries to approximate as much as possible these y values, which are also curved here on the two features, on the plane of the two features. But now if we project this back into our original space, so if we do the intersection between this transformation we did with our features and the plane we calculated here, we actually get a bent line because we bent the features when we did this nonlinear transformation. So this is the idea. We can use linear regression to fit a polynomial of degree 2 by doing this expansion and fitting on a higher dimension using the linear model. We can then increase the degree of the polynomial, do whatever we want, and this is very simple to do by just creating this data, these new features. So we saw how to do this using polyfit, fitting a polynomial. We load the data, we separate the feature vector and the target one, and now we fit a second degree polynomial and do the plot. But this is the same thing as doing this expansion and doing the linear, adjusting the linear model in this higher dimensional space after doing this nonlinear transformation to expand our features. So we can do this with by manually expanding the features, or we can use Scikit-Learn with this class polynomial features that allows us to do these polynomial expansions, and they are even better than simply the polynomial fit. Because when you try to expand, when you expand your data polynomially, if you have several features initially, then you can also have the products of those features and the raised to 2, to 3, and so on. So let's see a simple example here. Suppose we have this table with two features. So we have three examples. The first example is 1, 4, the second is 2, 5, the third is 3, 6. And now we want to expand this with a polynomial expansion of degree 2. And we can do this by importing from pre-processing on Scikit-Learn this class, polynomial features. And we use the object from this class. We specify what is the degree of the expansion we want. And then we transform our original data. So this fit transform method, this is something that you find quite often in Scikit-Learn. It basically tells us to compute the fit of whatever model there is. So in this case, there is actually no training and no fit, it just does the transformation, but then transform the data into the result. So this is what we get when we transform with polynomial features with the degree of 2. So we have here a constant value. This is an additional feature that is the same for all our examples, and this gives us an additional margin of flexibility to adjust the model. We have an additional feature that is simply constant. Then we have the original features. So the first one here, which is 1, 2, 3. The second one here, 4, 5, 6. Then we have the product, the square of the first one, 1, 4, 9. This is the first one squared. Then we have the product of the two. So 4 times 1, 2 times 5, 3 times 6. And then we have the square of the second one. So we are using this class, polynomial features, we can do easily a polynomial expansion of our data, and it does all these combinations. You can actually configure here, you have additional arguments that you can specify whether or not you want these cross combinations or this additional constant and so on. But this is makes it very easy to do this kind of expansion. So you can now use linear regression with, after this nonlinear expansion, to fit whatever curves you want. So let's see an example with the temperature data. The World Bank site has this programming interface that allows you to retrieve data for the average temperature of different years for each country. So you have this URL, and then you have the three-letter ISO code for the country .csv, and you can use that to download the data. And this is the file format. You have year and data, the labels for the columns, and then you have each year and the average temperature measured for the country. So one way we can get this, we can use this URL open method function from the request module, and this basically works similarly to the open function that we use when we are reading files from the drive. But instead of reading from the local disk, we are reading from a remote source. So we open the URL, and for that we use the base URL for the API, and then we add the ISO code.csv. Now this is something that is useful if you are using these values throughout your code. It's useful to create a global constant here so that it's more accessible, and you can update if the URL changes or something like that without having to dig through the code and check wherever it appears. So here basically we open this. This is now like a file object where we can read the data, and we can use from NumPy the gen from text, which reads a text file with a data matrix and returns that as a NumPy array. So basically we are using this object that gives us access to the remote data. We specify the delimiter, which is a comma, because these are comma separated values. And we also use this skip header to skip this first line here, because gen from text will try to convert everything to numbers. If you don't skip the headers, then you can get errors there. And now we have the data. An alternative is if we have the data in a file, a local file, we downloaded it first, then we can use pandas and use read CSV. So I supply this file in the archive with the data for this session, so you can do it like this. But if you want to use other countries, you can use this code to get other countries from the site. Okay, so here we can plot. We have the years from 1900 through 2012, and here we have the average temperature in Portugal over these years. So we want to fit a line to this data. We can use the linear regression from the Scikit-Learn, and we're going to read this file, the CSV files, and now we're going to get these two arrays with the years and the temperature. In many cases, especially with regression, when you're working with Scikit-Learn, these objects are expecting the data to be in each row corresponding to one example and each column corresponding to one feature. So if you give the data as a single vector with one dimension, then you get an error because the object does not know if that is one example with many features or many examples with one feature. So when we ask for the values in the year column, we get an array with one dimension. This is a vector. But we can use the reshape method of NumPy arrays to give it a different shape. And in this case, I'm going to give it two dimensions, so one column, and this -1 indicates that is as many rows as necessary. So this is a useful trick if you want to reshape your data. For example, you have one vector in one dimension and you need to put it in a column of a two-dimensional matrix. So you can do it like this. You reshape to as many rows as necessary and one column. I'm going to do that with the years and the temperature. And now I use the linear regression class to create an object. Note the parentheses there. I'm creating an object by executing the constructor of the class. And then this object, using the default arguments, I call the fit method to compute the parameters for the linear regression. So fit in Scikit-Learn is telling the object to compute the parameters to minimize the error function and obtain the parameters. And now the fit function returns also the object that was created here, but which now has the parameters adjusted. So this regression object now is the linear regression with the parameters computed using our data. So if I want to find out what are the predicted values from this this instantiated model here, I can do this predict. I can call the predict method in the object, give it the x value, so the features, and it will output the predicted values, the y values, which are the temperature in this case. So now I can create a figure and plot the original data, so the years and the temperature, and the predicted data. So I get the years and the predicted values. I plot the data with dots and a line for the prediction. I can also ask for the score of this fit. So after I fit, I can feed in data. I can use exactly the same data, for example, and I ask for the score when I apply this trained model, so the hypothesis that has the instantiated parameters, I apply it to this data. In this case of linear regression, what I get is this Nash-Sutcliffe efficiency coefficient, which basically looks at, it's 1 minus the ratio between the variances, the explained and non-explained variances, but basically 1 is the best, which is when the prediction exactly fits the data. 0 is what you get when the prediction is that everything is equal to the mean value. So if you use the mean of the labels and then predict everything equal to the mean, you get a 0 on this efficiency coefficient. And then if you are doing worse than that, you get negative values, and it can go all the way to minus infinity. So in this case, it's 0.58. It seems to be a good approximation, a nice score. And this is what we get here. So we computed the linear regression, and we have this straight line here. But if we want, we can use linear regression for adjusting curves to our data. So what we need to do here is we, instead of using the original years values, we are going to use that polynomial features class to expand our data to a polynomial expansion of degree 2, and we are going to transform the years value into that expansion. So now we're going to do this linear regression all the same, but now using the expanded value. So we have more features, and we are including x squared there. So we get this slight curve here, and we can expand more. So in this case, for degree 3, we now get this s. And if we look at the score that we're getting when we are measuring the score on the same data we use to fit the curve, it seems to be improving. So in this case, we had with just a straight line a score of 0.580. Then when we expanded to degree 2, we have 0.587. With degree 3, we now have 0.606. And so things seem to be fitting the data better. However, it seems to be better, but we are only looking at the data we use to fit the model. So we're going to see a bit later on in this lecture that this may not be a good indicator of how well our model is fitting. So let's leave this question in the air. Is this better or not? But first, let's look at classification. So classification is different from regression, because in regression we are trying to fit a line, or in general, in n dimensions, some hypersurface that is straight, a hyperplane, and we want it to be, if we are using linear regression, and we want it to be as close as possible to the data. If we are doing classification, we don't want these lines to approximate the data. We want to use them to separate the data into partitions, into different subgroups. So if we are using also a linear classifier, these will be hyperplanes, one hyperplane if we have two classes in n dimensions. These are the dimensions of the features. And we use the hyperplane to separate two sides. So one class will be on one side, the other class will be on the other. So one additional thing that we need for classification is this notion that the hyperplane has one side different from the other. So it's not something that merely adjusts the data, it's something that separates the data into subsets. So for a linear discriminant, let's consider a function of this type where we have these parameters, w here, and this is a vector which we do the inner product of this vector with the features that we have, and this will give us a value. Now, if you don't remember algebra, it's not a problem, but the idea is that the inner product will give you positive values if the vectors are pointing roughly in the same direction, or negative values if they are pointing away from each other. And so we can distinguish between one side of the plane and the other, and the plane that separates the two classes is the one where this here is 0. So if this expression is evaluated to 0, we are exactly on the frontier between the two classes. One side will be negative, the other side will be positive. So if we are doing this in 2 dimensions, we have 2 features here. This is an example of gene activity profiles of 2 different genes in normal cells and in tumor cells, so cancer cells. And in this case, we can draw a line separating this region where these genes have these activity combinations and this region where we have the cancer cells. We can do this in general in any number of dimensions. For example, in 3 dimensions, we would have not a line, but a plane. In 4 dimensions, I cannot draw that, but it would be a hyperplane and so on. And it's always the same idea. We have the plane that separates the classes is where this expression is 0, and one class is on the positive side, the other class is on the negative side. Okay, so this would be for a linear classification, and as a linear classifier, I'm going to use, for an example, logistic regression. So this is actually a bit confusing, the name, because it's called a regression because we are computing a regression to a function of the probability of belonging to one class, but it's actually a classifier because then we cut off at some threshold, say 50% probability of being in one class or the other, and we get the classifier because we are splitting the data into different partitions. So let's read the data. The data here for our cancer, the activation profiles for the different cells is given like this. We have 2 numbers for the activities of the 2 genes, and then we have a label 0 or 1 depending on the class where each cell belongs to. And now we can read the data. We're going to standardize the data. So this is generally a good idea because the data can come in different units or different scales. And if you are using those different scales, for example, you have one column in meters, the other in kilograms, the other in euros, then depending on the scale, you can get more weight for one feature, which is not realistic or reasonable. It's just because it happens to have larger numbers there. So one thing you can do is, like we saw before, we can standardize. We are going to subtract the mean and divide by the standard deviation, and then we can train a classifier. So in this case, I'm going to use logistic regression. For some versions of Scikit-Learn, there was a change in the solver. So if you don't specify the solver you want to use, you get a warning that it's going to use this solver as default. So basically, this is not doing anything other than silencing the warning. If you don't put this in some of the recent versions, then you get lots of warnings when you run your code. But you can just ignore here. This is a solver that is being used in the background. This is more important. This is weight given for the regularization. And regularization in logistic regression tries to put your frontier as far away as possible from where the most examples are. If you use very low regularization, then it looks or it pays more attention to those points that are close to the frontier. If you use a large value for regularization, give more weight to regularization, it will tend to look at points that are more further and further away from the frontier. So in this case, if you use a regularization of 1, there is an additional little trick here, because this C value is analogous to what is used in support vector machines. So actually the regularization weight is 1 over C. So if you put a C of 100, you use a regularization weight of 1/100th, and this is a low regularization. You get this result. If you increase the regularization by decreasing C, then in this case the frontier will shift closer to these blue ones, because there are lots of red ones close to the frontier, and it will try to move away from them. But okay, so this particular image, if you want to replicate it, has this parameter. So I'm using the logistic regression classifier to fit my data. So these are the features. The x's are these features, the coordinates for the points, and the y values are the labels. These are tumor cells, these are non-tumor cells, they have different labels, and this is what we get. We get the separation here between the two of them. Since logistic regression is a linear classifier, the separation is a straight line in this case, which works fine for this kind of data. But if we have a different data set, for example this one, then it doesn't work very well. Note that this one is not linearly separable, because there is no way of drawing a straight line here that will separate all the blue ones from the red ones. So because there is one here and some red ones are a bit overextended on this side, so you cannot separate them correctly with a straight line. So if we use logistic regression, in this case, we cannot get 100% accuracy on the training set, because there is no way of separating these two classes. We can do the same thing we did with regression, which is to expand the data. Note that there are other classifiers that you have in Scikit-Learn for which you do not need to do this expansion. So you can use random forest, support vector machines, lots of different things that don't need this kind of expansion. But if you want to use logistic regression, you can do it by using the polynomial features. For example, I'm going to do a quadratic expansion on the original features, the 2 features, and now I get a new table of features. So this one will have 6 columns, because that's the polynomial, the degree 2 polynomial expansion you get when you expand the 2 features. So this example I had here, this is the kind of expansion we are doing, adding this constant, the squares of the features, the product of the features, and the original features. So we get these 6, instead of 2 columns, we get 6 columns. And now we can do this with this quadratic expansion, and we get a slightly curved frontier. But we can increase this, for example, with 5, we get this frontier like this, and we are already separating them well. We can reduce the regularization factor to allow the frontier to come closer to the points, for example, by putting this in 10,000. Remember that the weight given to regularization is 1 over C. So now we have this sharper frontier here, well drawn between the points. So basically, it's the same idea. If you do some expansions like this, if you make your model more powerful, then you can adjust better to the shape of your training data. Now the question is if this is a good idea. For example, with this kind of data, would it be reasonable to predict that here should be a red point? Because it seems to make more sense that this part is blue and not red. So this is a problem when you start fitting too much to details on your data, and you can get some incorrect results. So this is the problem of overfitting, and how we can use validation to try to overcome that, to limit this problem. So let's suppose that we had this data originally. We are trying to fit a curve here, and in this case we have a straight line and it doesn't fit too well. So this would be an example of underfitting, where our model is not powerful enough to adjust to the patterns we have on the data. We can increase then the power of the model, do these expansions, polynomial expansions, and suppose we fit a polynomial of degree 3. Now we can follow this pattern better, but we still have some error here. So we are not, we cannot with a polynomial of degree 3 go very close to all of these points. So we can increase the power of the model, for example, degree 15, and now it fits very well the data. So it seems to come close to all the points. However, these parts here seem a bit questionable, because we would not expect to predict a value, a y value over here, for an x value in this place between these 2 points. So there seems to be something wrong with our model, even though when we fit it to our data, we can get very good, very accurate predictions for the data we used to fit the model. And this is a basic problem when you're using machine learning. You can improve the prediction of what you already know, but then you may sacrifice the ability to generalize beyond the data that you already have to new predictions. And since what we usually really want to predict is not the data that we already have, but something that is coming, new examples in the future, then we need to be careful about this generalization error. So let's look at the different aspects here. The training error is the one we're measuring on the training set. And the problem is that the training error is not a good indicator of how wrong our predictions will be for new examples. So in this case, we have a very small training error, but then we could be missing by a large amount the predictions for new examples. So we need to do something in order to compensate for this, or to check this generalization problem by looking outside the training error. So one possibility is to split our data, and we use part of the data for training. So in this case, the blue points were used to fit the curve, and then a random subset that we separated, we can use to evaluate the error outside the training set. So this, if we are just doing this, if we are just estimating the error outside the training set, we are using a test set. We are testing the hypothesis we obtained by fitting the model and seeing how much error this fitted hypothesis has when predicting new examples. However, we can also use this error outside the training set to fine-tune some things. For example, we have different models we can use, different degrees of the polynomial curve, and we want to pick the best one. So here it gives us, we have these 3 different concepts. One is the training error, which is the error we are measuring on the data we are using to fit the parameters. So if we want to compute the parameters for this curve and we are using these blue dots, this will be the training set, and the error measured on the blue dots will be the training error, because those are the points used to fit the actual parameters. The validation error is measured outside the training set. So this would be, for example, these red dots here. But we are also using it to optimize something. For example, we are checking the validation error in order to figure out which is the best model to fit our data. And then we have the test error, which is measured outside the training error, so on some test data set, but it's not used to choose anything. And this is important because in that case, the test error gives us an unbiased estimate of the true error. So the true error would be the average error over all the universe of possible points, which we cannot measure because we generally don't have the universe of all possible points. And the generalization error would be the difference between the true error and the training error. So it's how much we are losing when we go outside the training error. Okay, so but these are the really important concepts here. What the error you're minimizing when you're adjusting the parameters is not a good measure for how good your final hypothesis is, because you may be overfitting your data. The validation error, by measuring the error outside of the training set, can give you a good idea of how things are going and allows you to select the best model, the best regularization parameters, and so on. But then if you use this to select something to improve your results, then you cannot really use it as an unbiased estimate of the true error, because you already chose things based on this value, so it became biased. And that's why we usually set aside a subset of points just to get a good estimate of the error at the end when all the work is done. Okay, so one way of doing this validation part is just splitting into training set, validation set, and test set. But this has two drawbacks. One is that it gives us less data for training, because then we also, aside from the test set, we also need the validation set. And the other is that we are estimating the error for our model by just instantiating it once on one specific set of points and evaluating the error once on another specific set of points. Now, if the data was different, then maybe our model would behave differently, and we have no idea in this case. So cross-validation is actually the way we generally do this, which consists on separating. We can separate a subset of points for the final test if we want, but for cross-validation, we just use the training set. And we split the training set into a number of partitions, a number of folds. And let's say we have k folds, for example, 5 folds. And then we average the validation error by training our model with 4 of the folds, or k minus 1 of the folds, and measuring the error on the one that is left out. And then we repeat that for all the folds. So let me illustrate this with a diagram, because it's easier to understand. Let's say this is our training set, all of these points. So each point here corresponds to one point here. And now we are going to leave out this first group. So these are the large ones are left out. We're going to fit our classifier to the smaller dots, which are all of these. And we're going to measure the error in the training set, which are the smaller one, and also in the validation set. So this is the validation error, which is the ones that were left outside. And now we're going to repeat this, but leaving out these here. So we're going to train on all these ones, which are the small ones, and we're going to leave out these points here, the larger ones. And we are measuring the validation error here, and we're measuring the validation error now on this subset, and so on. And the average of these validation errors gives us an estimate of how well our model will perform if we train on this kind of data and then examine what it does outside the training set. So this gives us an estimate of the performance outside the training set when we train our model in this kind of data, and we have a sample of 5 different instances of training our model. So we can do this to try to prevent overfitting with Scikit-Learn very easily, because we have this function in the model selection module that is called cross-val score. So it does the cross-validation with our model and gives us the scores for each fold. So the validation score on each fold, basically it gives us this column here, the scores that we have for each validation. So here we can use this to see for our linear regression here on the temperature data. We can figure out if this is actually better than using a straight line or not. It seems better on the training set, but is it really better when we are trying to predict something outside the training data? So that's what we're going to do here. We're going to get our read the data from the file. So we get the two columns, the years and the temperature. And now for each degree from 0 to 5, I'm going to create a polynomial expansion of the years and then fit the linear regression. But I'm not just going to fit the linear regression to the whole set of data. I'm going to use the cross-validation score by running the same model, the linear regression, with different folds of these data. So these are the features and the target value, the temperature, using 5-fold cross-validation. So I'm going to do this kind of thing. Split the data into 5 groups, leave one out, train with the rest, measure the validation error, so the error on the one that was left out, and keep changing the ones that are left out and computing these validation errors. So I get 5 validation errors by doing this cross-validation score, and now I'm going to print the degree I'm looking at and the mean of the cross-validation scores. So one thing we can see here is that even though our model seems to be pretty good on the training data, when we actually measure the performance outside the training set, we get much poorer results. And another thing we can see is that if we use a degree of 0, then it's very poor, but the degree of 0 is just a constant. So we are just trying to fit a constant value to that that set of data, and this doesn't work very well. But if we use an expansion of degree 1, which is just the original data, we have a much better performance. That is, this measure is not as negative as it is when we increase the power of our model. So we can see that if we use degree 2 or 3 or 4 or 5, we're actually overfitting the data, and we're getting poorer performance. So this is an important thing that you should do when you are fitting models to your data. Get a good measure outside the training set if what you want is to predict things outside the training data. So if you just want to fit the model with the training data, then you don't need to worry too much about this. But if you want to predict something for new examples, then you should be careful with this overfitting problem. So to sum up this part, machine learning is a very powerful approach in general if you have the data, because it allows you to find patterns in the data and to make inferences without explicit rules, without having to know the explicit rules for those conclusions. And it's very easy to use with Python because Scikit-Learn gives you access to lots of different classifiers and regression models. So you have other regression models there, lots of different classifiers. If you look at the documentation, you have many different options here. You just need to be careful of the details and what kind of problem specifically you're trying to solve. And in particular, remember that the error estimates with your training set, with the data that you use to fine-tune the parameters, and also to a smaller extent, the estimates of the error when you use for validation and you use them to choose the best options. These are not very good estimates of the true error. So you need to have some data left over to do a final estimate of the true error and check how good your model really is, because everything you're using for fine-tuning may give you the illusion that your model is better than it actually is. So check out the documentation in Scikit-Learn, and this was just a brief introduction for if you need to use Python to do this kind of supervised learning. Let's have a 10-minute break, and then we're going to look at unsupervised learning So at 6:05, I'm going to start the next lecture. See you soon.